Hi everyone. This video covers 6.7 Convergent series and sums to infinity. Okay, don't let the title scare you. They're actually very easy, and it's actually pretty interesting. So by now we have came across arithmetic and geometric series. We're gonna explore a little bit deeper with geometric series, okay? And then later on, and that's going to lead us to something that's called the convergent series. And then after that, we'll be looking at sums. Sums means adding up, right? So we're going to keep on adding, and we're going to add until infinity. All right, so that's pretty cool. Let's get into it. All right, so here I have two series over here. Series meaning we're adding stuff up, right? I want you guys to pause the video and kind of look at these two series and see if there's anything that you can pick up from them. Okay, so just keep in mind that this plus dot dot dot, plus dot dot dot, that means I'm gonna keep on doing that until what, right? Until what? Anyways, pause the video and see if you can pick up something interesting for each one of them. Alright, welcome back. So, a few questions for you. The first one, are these series geometric or arithmetic? Are these two series geometric or arithmetic? I hope your answer is geometric, okay? Because you can see that 128 to 64, what do? We multiply by half. 64 to 32, I multiply by half. 32 to 16, I multiply by half. So this is obviously a geometric series. And then my R for my first geometric series would be half, 1 over 2. Now what about the second one? 128 becomes 256, that's multiplied by 2. 256 became 512, that's multiplied by 2. 512 became 1024, that's multiplied by 2 again. So this is also a geometric series, and my R is equal to 2. Right? Multiply 2, multiply 2, multiply 2, so on and so forth. Okay, so the third question, how does each term change as the series progresses? Right? So if this keeps on going, what happens to the value of each term? Is it getting bigger? Is it getting smaller? So for the first one, because every time for me, in order for me to find the next term, I multiply by half. From the next term, I multiply by half. So as the series progresses, the value that we are going to add becomes smaller and smaller. So eventually over here becomes a fraction. So this is half, a quarter, 1/8, and then it becomes smaller and smaller. For the second series, because my R is equal to 2, so times 2, times 2, times 2, times 2, times 2. So every term becomes bigger and bigger. Every term becomes bigger and bigger. So that's what this question is asking. The first one, the individual term becomes smaller and smaller. And the second one, the individual term becomes bigger and bigger. Okay, now, what do you think? AN, the nth term. What do you think the nth term will be in each series? Okay, so let's take the first one. The individual term, as we already discussed, it's going to become smaller and smaller, right? So this is one became half, and then the next one is 1/4, and then 1/8, 1/16, 1 over 32, and it becomes smaller and smaller and smaller. What do you think the last term is going to be? Right, just kind of imagine that a little bit. The last term, is it going to be a very big number, or is it going to be a small number, or it's actually a very, 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 very small number? Right? Because we're going to keep on multiplying by half, so the nth term should be pretty small. Now the question would be how small? Right? If you look at the second series, where my R is equal to 2, what's my nth term going to be? Is it going to be something small? Is it going to be something big? Or or is it going to be something that's very, 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 very big? Okay, so think about this kind of. Just you need to use a little bit of imagination, and just be creative. Now, this is kind of the key question for this video. Would it be possible for us to find the sum of all the terms until n infinity, which is the last term, the very last term, right? So, is it possible for us to do that? So if you think about it, my first term, let's look at my first series over here. My first one is 128, second one is 64, and then as the series progresses, my individual term becomes smaller and smaller. So eventually, even though the series is not going to stop, but it is as if it's so small that it becomes almost insignificant. It's as if we're not really adding anything to it. Okay, so when that happens, we have a converging series, because eventually the individual term in the series will become so small that it is almost insignificant. Whereas the second one, can we actually add it? If you think about it, 128, 256 times 2 times 2 times 2. The individual term becomes bigger and bigger, right? So towards the end, the number is going to become so big that it doesn't really make any sense to add them. You see the point here? Right, so again, use your creativity a little bit, use your imagination a little bit. The first one, let's say towards the end, there's no end, because this series is going to keep on going. But just imagine, let's say we're so far down the series, the number is going to become so small, right? So small that it's as if we're not adding anything. Whereas for the second one, we can't do it. We cannot add the sum because the number becomes so big, right? The number becomes so big that, how big? Very big, super big, right? So it doesn't really make sense to add something so big with something so small. So in the end, we just have infinity, right? But the first one, if eventually we're not adding anything more, eventually it's going to look like as if we're not adding anything else to the series, then maybe we actually can come up with the value for that. Does that make sense? Anyways, this is the concept of convergent series and sums to infinity. Okay? This is the concept. Now, the concept can actually be quite interesting, right? Just as long as you use imagination a little bit. Now, just keep in mind, we are only interested in the convergent series. We're only interested in the ones that eventually become so small that it's not going to really make a difference. Right? So we're looking at convergent series. Series like the second one, we call them divergent series because they don't tend to go towards any value. You just keep on becoming bigger. Right? So we can only calculate the sum to infinity for converging series. Now, what's the R value for convergent series? Now, the first one is convergent series. My R value is half. The second one is not. My R value was 2. So what do you think my R value has to be for a converging series? It has to be a fraction. It has to be a fraction, okay? It can be positive, it can be negative. It can be positive fraction, negative fraction, but it has to be a fraction. So when you're asked to find the sum to infinity, as shown here, this is sum to infinity. The first thing you need to check is it a convergent series? Is it something like that? The first one over here. If it is, what's your R? Right? So use your R value to find if it's convergent, and if it is a convergent series, then we can carry out to continue to find the sums to infinity. Now, this is simply the formula, and this is also in your formula booklet. Your A1 is your first term, your R is simply your common, the R that you calculate that brings you to the next term, right? The R value. Alright, so let's say today I want you guys to write this down somewhere on your notebook. So my S infinity is equal to A1 over 1 minus R. Okay? Now, if you want to know how to get the formula, come and talk to me. It is actually pretty cool. Alright? Come talk to me if you want to know how they got this formula. But what I do want you guys to be, what I do want everyone to be able to do is to apply this and verify that it's a convergent series. Okay? Alright, let's take a look at some example. Here I have 18 plus 6 plus 2 plus blah blah blah. The first part they want us to define S of 15, and the second one is S infinity. So here I have copy and paste the question, the example, on a whiteboard. So let's try to solve this. The first part, S15. So my S15, this is geometric or is this arithmetic? Let's verify that. So 18, 6, 2. It seems like my R is equal to how much? My R is equal to 1/3. Is that right? Which means it is a convergent series. So S15 is equal to my A1, which is 18, multiplied by my 1 minus 1 over 3 to the power of 15. Right? So I'm just simply applying the formula. Not the S infinity formula, it's the sum, the Sn formula, right? Over 1 minus 1/3. And if you put that in your calculator, you'll be getting something close to, I'm gonna say, I think it's 26. It's actually very close to 27.0, right? 26.99999 something. You put that in your calculator. Okay? Now that's my first part. My second part, S infinity. Now this is a convergent series, right? I know for sure because my R is a fraction. So my convergent, now I can simply apply the formula. My A1 is 18. A1 is 18 divided by 1 minus 1 over 3. I'm just following the formula at the bottom right of this screen. So that's 18 divided by 2/3. And that's gonna be equal to 18 times 2 over 3. Actually 3 over 2. This is 1, this is 9. The final answer is 27. Okay. And this is not rounded up. This is exactly 27. Which is pretty interesting if you think about it. Because 18 I multiply by 1/3 to give me 6, multiply by 1/3 to give me 2, the next one is going to be 2/3, and then that keeps on going. And if I keep on adding that for infinite many of times, I'll get 27. You see that? In fact, for my S15, let me just put down the value for my S15. It was if you have your calculator with you, you should actually put that in. It's 9, how many 9s? I think I have 5 9s. 9, 9, 9, 9. And then I have 8, 1, 2. 8, 1, 2, and then blah, blah, blah. Right? So, when I'm adding up to the 15th term, it was already very close to, as if adding up to the 20, to infinity. Okay? So, which is pretty intuitive. This is pretty interesting, pretty intuitive, right? Alright, I hope you guys find this video helpful. Make sure you know this formula right here, and we'll come across a few examples in class. Okay? See ya.